Hello, everyone. So I'm Zheng, I'm from Georgia Tech. Today I'm going to present TRIDENT, and this is a joint work with Dr. Landen, Matthew Landen, and Professor Roberto Perdisci, and Professor Wenke. So my friend Nicole was watching a superhero movie on a free streaming website last Friday. So suddenly, an in-page notification popped up asking her to check her Mac. And she was thinking, this must be a fake message because she was using a Windows laptop. Then she clicked the skip ad button. Unfortunately, this click brought her to a website saying her Windows was infected. And she was panicked and did not even give a second thought. So she called the number, and the technician asked her, hey, purchase a protection plan so we can fix this problem. And Nicole gave her credit card number to the technician. So a few days later, so Nicole told me this story, and I said, sorry, Nicole, so you were scammed. So how do we help Nicole to defend against such online scams? So a paper published in NDSS 17 analyzed the tech support scam like this and found malvertising is a major culprit for exposing users to those scams, and they proposed countermeasures. Although this study is useful for alerting users for tech support scams, so this is far from enough because there are more. So for example, notification spam, scamware, price scam. So we can see security researchers have been publishing papers studying each individual type of web-based social engineering attack. However, are we going to build detection models for each type of the attack specifically? Of course not. So this is unrealistic and is not a scalable solution. So to find a scalable solution, so we were thinking, why not focus on the leading cause of these attacks? So based on our prior study, we discovered that in order to launch social engineering attacks at a scale, attackers rely on low-tier ad networks. So these low-tier ad networks usually pay more than big names such as Google to attract ad publishers to use their services. Unfortunately, these services become vehicles for distributing social engineering attacks. For example, they inject strategically crafted DOM elements, such as the invisible overlay and the misleading content, such as the skip ads button. So when interacting with those DOM elements, which we call it social engineering ads, so usually users are taken to websites that contain social engineering attacks. So given this social engineering attack distribution model, so the key idea of detecting and blocking social engineering attacks is to adopt an indirect approach. So in other words, instead of inspecting the landing pages one by one, so we focus on the leading cause, so navigation initiated by the user clicks, so that we can cut off the path to the social engineering websites. So you may wonder, why not use ad blocking tools, since those attacks are distributed by ad networks? So unfortunately, these solutions are not effective. We looked at two state-of-the-art solutions, one block-list-based and one machine learning-based. So first, we tested the Brave Shield, which is the ad blocking module for Brave browser. So the false negative rate is around 15%. Then we look at the ad graph, which is the most recent machine learning solution for blocking online ads and the trackers. So we trained the two models using ad graphs features. So one is trained using the generic ads data set as stated in their paper, and the other is trained to use the social engineering ads data we collected. So both of their performance degraded by almost 10% compared with its original model. So these two evaluations tells us social engineering ads can evade state-of-the-art ad blocking tools very easily. So this is because social engineering ads are not the traditional ads. They behave differently than generic ads or benign DOM elements. So for example, they are often in the invisible form or appear as misleading content. So the code that injected those content can be obfuscated and harder to analyze. So not to mention that low-tier ad networks often updated their script URLs to evade blocklist. To address these challenges, we introduced TRIDENT, an online system for identifying social engineering ads and blocking navigation to potential social engineering websites. So TRIDENT instruments Chromium and builds a social engineering agent inside the DevTools protocol inside the Blink, which is the rendering engine. So when the navigation event takes place, so TRIDENT examines the cause of this navigation and determine whether to proceed. So to achieve this, TRIDENT monitors JavaScript actions of the web page. So for example, recall this movie website. So the malicious ad scripts insert an invisible overlay, creates the malicious skip ad button, and also registers mouse click event listeners to hijack clicks. So TRIDENT relies on the social engineering agent to monitor these events, such as the JavaScript function calls, DOM manipulation, and network communications. So while collecting those events, TRIDENT builds a web action history graph to describe the activities on the web page. So for brevity, I'll just introduce the one key component of the graph here, and you can refer to the paper for more details. So the component I'm gonna introduce here is the navigation initiator. Because TRIDENT focuses on blocking navigation to the social engineering websites, so it needs to know what initiates the navigation. So the first type on the left is initiated by the JavaScript function. For example, a malicious script registers an event listener, which listens to the mouse clicks on the whole viewport. So the listener then opens a new window to load the social engineering web page. So the TRIDENT can just query this JavaScript stack frame to obtain the responsible actor. And this is in line with the previous work. So the unique part in TRIDENT is the second type navigation, which is through clicking links. So for example, a malicious script inserts a link that points to a malicious website. However, when navigation starts, there is no JavaScript running because click a link is a user behavior. So TRIDENT memorized the URL when the link was inserted. And when the navigation happens, so it checks whether the opened window matches to the inserted link. So if yes, TRIDENT connected the function which inserts the link with the opened window using a dotted line. So such attribution allows TRIDENT to find every responsible actors of a navigation event. So once the web history action graph is built, so we convert the graph to the feature vectors. So we conclude with 3 feature vector groups to model the JavaScript actions. The first feature group is property features that describe what the JavaScript code is. So those features are extracted from the properties of the nodes. And the second is the action feature group that monitors what the JavaScript code does. They are extracted from the path of the graph. And the third is about the consequences features that observe what the JavaScript code causes. They are extracted from the properties of the edges related to the navigation. So TRIDENT used these features defined in these 3 feature groups to build a classifier. And the details of the feature list is in the paper. So now let me give an example of how TRIDENT blocks social engineering related navigation. Recall this video website. So first, this ad publisher compiles an inline ad script. This inline ad script registers a callback. After several seconds, the callback registers an event listener to listen to clicks on the whole document. So meanwhile, the inline script also includes a third-party script, so which registers a callback using the Saitama API and remove the event listener. So for each action, TRIDENT updates the graph and extracts the features out of the graph in the real time. So when the user clicks the skip ad button, which triggers the navigation, so TRIDENT concludes the feature list and run its classifier synchronously. So because of these behaviors are malicious, TRIDENT blocks the navigation. So we started crawling more than 100,000 ad publishers which use low-tier ad networks. So in January 2022, we first trained TRIDENT with the collected data. There are 1,479 social engineering attacks identified with our semi-auto labeling techniques, among about like 260,000 of navigation events. So TRIDENT was trained with a random forest classifier and achieved over 92% accuracy with 10-fold cross-validation. So in October 2022, so we collect another batch of data to test the TRIDENT's performance over time. So as a result, TRIDENT also achieved a very high performance, indicating we don't need to retrain TRIDENT often. So once a year is enough. So TRIDENT was trained on a diverse data set that covered more than 10 lower tier ad networks such as Adstera and PopCache, and including the top tier ad networks such as Google, Facebook, and Amazon. So we labeled the data set with a semi-auto approach that combines the results from the categorical block list and the image clusters of a landing page and reviewed by human. Then we found 6 types of the social engineering attacks with using that labeling approach, including unwanted software download, and dating scam, price scam, and push notification spam, and scareware and text support scam. So the details of the labeling techniques is in the paper. So when testing TRIDENT, we achieved about 2% false positivity rate. After analyzing the causes, we found 3 types of false positives. So the first one is that the ad scripts from @this.com inject the DOM elements onto the mainframe on purpose for sharing the page, like the icons you might have seen on the internet. To reduce these types of false positive, we can adopt an allow list approach. And the second type is that the malicious ad script actually did inject the social engineering ads on the page, but when interacting with those social engineering ads, the crawler we built was brought to take it into like Google or Yahoo, because we are intensively crawling those page, and they probably put our IP in the block list. And the third type of false positive is that, okay, they inject social engineering ads, but interacting with the ads, the crawler was brought to adult website. So for false negatives, so we only found one case, which embedded a malicious link as a first-party content appear as an image in the website, and that image leads to a malicious software download website. So moreover, so in the testing data set, TRIDENT also identified social engineering attacks distributed by two unseen low-tier ad networks, so pop ads and pop my ads. So more details are in the paper. Now I want to discuss what if adversaries know how TRIDENT works and try to evade TRIDENT. Due to the limited number of the evasion examples found in the wild, so we studied the evasion with simulations. So based on our domain expert intuition of the feasible techniques, we summarized the 4 guidelines. The first, to use the malicious script as a first-party script, and the second is to put it as an inline script. And third, taking the user to the social engineering websites without the redirects. That is to simulate clicking benign links. And the last one is to behave as the benign scripts, which means do not manipulate the DOM at all, or just a few manipulation. So from the table on the right, we can see only when the malicious script becomes the first party and it does not incur any redirects, it can have a high, like 9% evasion rate. Unfortunately, this is highly unlikely in the wild because it requires the attacker to collude with the ad publishers. And attackers cannot achieve this by using ad networks for attacks at scale. So we implement TRIDENT in the Chrome DevTools protocol with less than 800 lines of C++ code, which only incurred around 2% runtime overhead when browsing the internet, and no CPU, no memory overhead. So to conclude, so we proposed a novel online system for indirectly detecting and blocking social engineering attacks on the internet, and it achieves 92% accuracy, which outperforms the state-of-the-art generic ad blocking tools by more than 10%. And also, it is robust to evasion attempts. I'm happy to take any questions.